Ok, è la registrazione della seconda parte della lezione di 4 novembre in cui cercheremo di vedere l'esempio di Kuramoto e vedere vicino ad alcuni punti stazionari il comportamento della soluzione. Prima di iniziare vorrei fare una piccola simulazione con Kuramoto, così possiamo vedere come si comporta, perché il corso di Mathematics for Neuroscience for such important model requires kind of really have not only close to stationary points, but have a general picture. And if you don't mind, let me switch on to Mathematica. That is, 1 second. We have appunti to share equazioni ordinarie. No, Matematica. Okay. We had stream plot. This is the command stream plot. Actually, in internet, you can find the site where putting one command, you can put gratis this application. Alpha Wolfram is the keyword you follow in Google, Mr. Google. So if you write Wolfram Alpha, you can find the page where in one window you can put your command. In this case, I put the command stream plot, and then the picture appeared. For example, we have our now let me share the screen so that you can find for Kuramoto the right share the screen, il tuo schermo interno, ok, share. So, very good. Let me put window magnification 200. So, all these guys, they are not necessary. Good. We need only one line for our software. And our two functions are sine. Can you help me? The first equation in Kuramoto that we wrote yesterday, theta 1 prime was equal sine of theta 1 minus theta 2, or minus sine of theta 1 minus theta 2. Okay, therefore I shall put this minus. You can see it. I'll save as, we shall call this file Kuramoto 1, because we shall have several simulations. Our theta 1 and theta 2 in this case shall be x and y. This is question of x minus y. So we have minus sine theta 1 minus theta 2. Thank you. And the other guy was sine of x1 minus theta 1 minus theta 2. X minus y. You can follow what I am doing by internet. So we are trying in larger domain to see what will happen. And this is really, as you can see, the picture is very clear what we are doing. Actually, if we speak about pi, because in our exercise we had pi over 2. Pi is 3 point something. Pi over 2 is 1 point something. So one of the points on this picture. The picture first shows that all trajectories are lines. This is something very, very interesting. Probably in this case, we have a very simple model. And in this case, the situation is really very, very simple. And for example, if you take 0, 0, you see 0, 0 point in our picture. It seems that all trajectories, at least with arrows, they go towards 0, 0. Can you see on the software? No. Ah, okay, okay. Because, okay. So this is kind of very good help. This is kind of very nice helping picture. And this really poses the question, this is very simple model then, when we have only 2 oscillators. The situation shall be much more interesting when we have 3 oscillators, and then you have a more interesting picture. But since we decided to work with 2 decays, with 2 phases, let us see now our calculation, what we'll do. For we had 0 as a stationary point, so we have to clean finally let me stop the sharing and let us make some calculation. Okay. Okay. This is done. Be a little bit. Okay, hope it is working. So instead of theta 1, theta 2, I shall use x, y as in the software. So we have x prime was minus sine x minus y. Y prime was sine of x minus y. And we said, let us take in the point A, it was stationary point 0, 0. Yeah. So let us take x 0 equals 0 and y 0 equals 0. So this stationary point is given. And we have to make for F1 Taylor expansion. F1, this shall be our F2. F1 in XY, the Taylor expansion starts with F1 in 0, 0, but in 0, 0 it is 0. So we shall not write this guy. We start with the X F1 in the point 0, 0 times X. Since x0 is 0, this is only x, plus the f in 0, 0 times y plus a remainder. And of course, now we can calculate, sorry, this is f1, because we made Taylor expansion of f1. So what is the derivative of minus sign? Derivative of minus sign in x shall be, the derivative of minus sign is minus cosine. Minus cosine, in which point? 0, 0. Cosine of 0 is 1. Minus cosine of 0 is minus 1. So this guy here is minus 1. When you take derivative with respect to y, you fix x and differentiate with respect to y. We have derivative of sine is cosine. We have 1 minus, 2 minus, because when you differentiate minus y, you get another minus 1. Therefore, the derivative of this guy shall be cosine of 0. But cosine of 0, you said this is 1. So we get our Taylor expansion, minus x plus epsilon. Let us do the same thing with F2. Here I shall make small trick again. F2 is minus F1 because I change only the sign. So what I have to do, I have to put instead of F2 minus F1, and this is computed. Minus this guy gives 1 times x minus 1 times epsilon. Why? Because this is minus F1. So I take this expression and multiply by minus 1. That's all. And we get immediately the Taylor expansion for F2. So what is our linearized system? Finally, from here we get linearizing. If you want, formally, we have to do the same thing that we did in our previous example. So we shall call x u and epsilon v. Why? Because x epsilon solve this system where eventually we have remainder. When we kill the remainder, the solution probably is slightly different. That's why we put u and v, because our new system, u prime, is equal minus u plus v, and v prime is equal u minus v, is very similar to this, but in this system we cancel the remainder in Taylor expansion. That's why rigorously it's better instead of xy to use u and v. If instead I have x0 equal p, that my u shall be x minus p. This is what we did in the previous example. Okay, now we have our system 2, and we have our matrix A, that is minus 1, 1, and this is 1, minus 1. What you can say about this matrix? Sorry, this is minus 1. I was thinking about minus lambda. A minus lambda. So, how you can find...
values are negative.
Yes, these are negative, but eigenvalues, they are A minus lambda E. This is minus 1 minus lambda, 1, 1, minus 1 minus lambda. Therefore, we have determinant equals 0. But this determinant, you can compute. This is, if I change this by this, what is this? This is 1 plus lambda squared, because we have always minus. So our characteristic equation is 1 plus lambda squared minus 1 equals 0. This you can solve very easy. One root is lambda equals 0, and the other root is lambda equal minus 2, if I'm not mistaken. So lambda 1 is, for example, minus 0. Lambda 2 is minus 2. For this diagonal system, we already had, this is the degenerate case. We cannot say focus, center, or saddle point, because our classification was only for the case when both eigenvalues are not 0. If one of them is 0, this case is degenerate. That's why our picture was degenerate and we had these straight lines. So what will happen with this system? For example, in this case, yesterday we made kind of a picture. If you have For example, this system we can say u prime equal, first eigenvalue is 0, v prime equal minus 2v. This is the diagonal system when we have eigenvalues 0 and minus 2. And for this, we already have the picture. If this is u, if this is v, u prime equals 0 means u is a constant. If u is a constant, then we shall have such line. U constant is such line. How we solve this? V prime, this vt is v0 a to the power minus 2t. And we can immediately say, if I start from here, of course, v0 is 0, and this is the point that is not is solution. Solution is staying always in this point. But if I start from here, what will happen with v? U is a constant, but v is decreasing or increasing. Here is v0. If I take v0 here, then we shall go in this direction or up. We shall go down because when t goes to plus infinity, this guy goes to 0. Therefore, from here, I have to put the arrows in this direction. And if I start with v0 negative, everything changes. We have this, this, this. And you see how degenerate is our picture. This is the case when we have diagonal matrix. What we had on our real situation, remember, let me share again the screen in order to show you the real situation. Okay. As you can see, the picture for the real situation was a little bit different. Let me put here the picture. The picture was something like this. Here is this guy, and here this is approaching, this is approaching. So, as you can see, the picture for this system 2 is different from the picture for this system 3. But the pictures are similar. What we have done, simply this x is slightly rotated. And if you rotate, you get this picture. That's why, in order to answer to your previous question, what is first eigenvalue, what is second eigenvalue, for me, this is sufficient because I know that the general case, that is, let me stop sharing and go to our pictures. If we compare this picture and this picture, we say that the second picture is obtained from this one, making small rotation. And you get, this is our, how to say, each point of this line is, the point is trajectory. So if your initial data are here, your solution is not going outside because v0 here is 0 and remains always 0, while u is a constant. So if you start from this point, you stay all the time in this point. But if you go slightly above, from here, for example, then your solution, thanks to this property, v0 is positive, is going to 0 exponentially, and when t goes to infinity, you approach this point. Of course, for our written exam, it shall be sufficient to make this picture and say this is degenerate. If one of these guys is 0, this is degenerate. stationary point, and it is sufficient for this degenerate stationary point, say that your trajectories, for example, for this case, you take your eigenvalues, put in the system, and build this picture that we already know. That is a picture that after rotation shall give the real situation. So this is something very important for our Kuramoto model.
Professor?
Yes?
I didn't get how we formed the third system.
How?
We formed this third system.
How? Simply, we take these two eigenvalues, and I said, suppose our system is with diagonal matrix, and on diagonal you put eigenvalues without caring who is first, who is one. If you take lambda 1, 0, the second guy -2, then you simply take diagonal system. So you take from here lambda 1, 0, 0, lambda 2. For this matrix, you construct this system and you study this system. For me, this is sufficient to study the diagonal system after finding the eigenvalues. You find your eigenvalues, you build diagonal system with lambda 1, lambda 2. In this case, lambda 1 is degenerate. And then for this system, you construct UV with this diagonal system, diagonal matrix. Because what is the matrix for this system? The matrix is 0, 0, 0, -2. And this is exactly what I said, lambda 1, 0, lambda 2, -2. Probably still it is not clear.
No, it's okay. Thank you.
Okay, very good.
Professor, so you made a simplification.
Yes?
But by your assumption, you are making a simplification.
Which assumption?
This thing about the diagonal system that you were...
Yes, we made simplification. That is very modulo rotation corresponds to the real situation. Exactly.
Okay.
This simplifies essentially the things. But as we have seen with many numerical simulation modifying our matrices, we have seen that if you know the situation for diagonal case, then you know the situation for system 2, because we have a general theorem that says that given any matrix A, we have this U -1 diagonal U. This we have already seen that it is possible starting with a matrix, any matrix, find the invertible matrix U, so that here we have diagonal matrix or Jordan block. Thanks to this theorem, we can say that this U, in most of the cases, can be done as rotation, can be interpreted as rotation. But this theoretical part that I don't think to plug inside the written exam. If we discuss the oral exam, then I shall ask this. For the written case, it is sufficient that you understand the diagonal part, because thanks to this relation, the generic case for any matrix can be reduced to the case of diagonal matrix. This is the justification, a little bit more rigorous. Okay, if this is clear, let us see other questions. Okay, then let's me add a small thing connected with our system, Kuramoto system, because we already mentioned really very nice structure. But this nice structure we could see also, and this is typical for Kuramoto. I think other stationary points, now we studied one stationary point, 0, 0, the other you can do in similar way to compute. Of course, we can turn back to these things again during exercises, but let us now explain what we can do for our system of Kuramoto. Here there is very simple operation that we can do. Take the sum of these two equations. Why? Because you see minus sign, plus sign, the sum gives cancellation. Therefore, taking the sum, we immediately get x prime plus y prime equals 0. And this gives you important rule, xt plus yt equal constant. This explains why on our picture we have straight lines, because the equation x plus y equal constant is equation of a line. So this means if you take the sum of your two faces, this shall be a constant. If you know this value in the point t equals 0, if you know x0, y0, then x plus y shall be determined by this initial value of x0 plus y0. And this is important relation. So if we use this, we can, for example, consider the case of x prime, y prime, and zeta prime. Three faces. When we have three faces, what will happen? Of course, we have now minus sine of x minus y, then we have minus sine of x minus zeta. So what I am doing, I am writing kind of x. If here is I have x, I leave x here. When I have y, this is minus sine, and y minus x minus sine of y minus zeta. And if we have zeta, this is minus sine of zeta minus x minus sine of zeta minus y. This is the case of 3 by 3 system. What we can do here? You see, here I have minus sine x minus y. What I have here? I have minus sine y minus x. Of course, if I exchange these two guys, x minus y, minus shall be outside, and I shall have plus sine minus sine. So, if I repeat the same operation, the same addition, adding all equations, what will happen? We shall have x prime plus y prime plus zeta prime is equal. This cancels with this. X minus zeta, this is zeta minus x. So these two guys cancels. And again, we have cancellation of these guys. So this is important that the sum of the faces is a constant. And this is very important thing for Kuramoto. So we can say in this case, xt plus yt plus zeta t is equal constant. This relation enables us to turn back to our equation and say, oh, this is not important, but whenever I have zeta, I shall write constant minus x minus epsilon. Therefore, now we can introduce more realistic Kuramoto system with 3 phases, which are actually 2 phases, because the third one is a constant minus the sum. And we can simply say that our new system for x, epsilon, and zeta shall be, you look this system, shall be x prime is equal, can you see here? I hope you can see here, x prime is minus sine x minus y, and here we have x minus zeta. Let us compute x minus zeta. I substitute zeta here, so I have x minus c plus x plus y. So this is 2x plus epsilon minus c. And I have to write minus sine of 2x plus epsilon minus c. Epsilon prime. What is epsilon prime? Minus sine of epsilon minus x. And then we have epsilon minus zeta. But epsilon minus zeta is quite similar. This is x plus 2 epsilon minus c. Similar calculation. We exchange x and epsilon. So I have minus sine of x plus 2 epsilon minus c. This is my new system, which is much more effective.
Excuse me, I cannot see.
You cannot see what?
The last, yes. Yes, that system.
Now it's better seen, or?
Can you write a little bit bigger, because I can't read.
Okay, let us write, but we need a little bit space. So I shall cancel this part, and I shall write x prime is minus sine of x minus y minus sine of 2x plus epsilon minus c. This is better?
Yes, thank you.
Okay, and epsilon prime is minus sine of epsilon minus x minus sine of x plus 2 epsilon minus c. This is our system. And if you want, we can take this constant c, for example, equal, if this is sine, we can take, this is much simpler. If you have pi, then you can simplify. You can take also c equals 0. Even this is much simpler. If you take c equals 0. What does it mean? That all faces have sum. 3 faces has sum that is 0. And this is very important. This is so-called barycenter of x, epsilon, and zeta. And it is 0. So this is our 2x2 system. And of course, this is slightly different from the case when we have 2 oscillators. Our third oscillator zeta, how is defined? Zeta is the constant that we have chosen 0, but this is minus x minus epsilon. So this is the model of 3 phases, such that the third phase is expressed in terms of these two phases. And I would suggest you, for the preparation, to consider this case. Of course, in our next appointments, we can try with this Kuramoto 2x2 system and see the picture first with software and then with these Taylor expansions to see around some critical points, stationary points, what is the behavior of Kuramoto. With this, I think this is the practically the final part of our appointments for deterministic approach based on models with differential equations. I think from the next time we shall start to see how we can have statistical calculations with some data and then introduce probability elements of probability. But concerning the probability, you had some preliminary courses you followed for probability, or this is the first time we shall speak about probability?
I had one course of probability.
So this is something that probably is much closer to your previous. Oh, then I shall be very grateful if some of you, if you followed some course on probability and if you have the program, only the program of the course, to send me to say, or during the course we shall see if you have seen what I am doing, then we can eventually simplify or arrange our course accordingly. Okay. So let us see if you have some questions. I think now we can stop the registration and remember from tomorrow around 12 o'clock you can start the simulation. We always shall have in our next appointments kind of 15-20 minutes to return back to make exercises, not to forget this, because if we switch to probability, you shall forget what is done till the moment. Therefore, let us make the simulation and then I shall return back to some exercises connected with these topics. Then, thank you for your attention. Let me stop the registration.